So good morning. Before I introduce Sergio Verdu, who will introduce David Tse, I'd like to make a last-minute announcement. Now here, last-minute announcement means that we don't have a slide to go on the screen. So, but we will have signs downstairs to indicate. What we're doing this morning in the very first session, so that's 9:50 to 11:10, is we're making a swap. We're swapping universal compression, which is currently scheduled for room 203A, and we're exchanging it with estimation 2, which is currently scheduled for 210. So if you were a speaker in either of those two sessions, that's universal compression, TA1-3, or estimation 2, which is TA1-8, there'll be a new room. It'll be indicated downstairs. So universal compression will be in room 210, and estimation 2 will be in room 203A. All right. So without further ado, let me introduce Sergio Verdu.
Hello and good morning, everyone. Actually, Rob introduced our speaker yesterday, Rich Baraniuk, and he forgot to add one famous Canadian to the list, and that famous Canadian is David Tse. It's very easy to introduce David, but not so easy to introduce him without running out of superlatives. He's been an enormously influential contributor to the world of wireless communications, and one of the most prolific contributors to our transactions on information theory. I think if he were to publish his greatest hits, I think by now it would be a 2-volume compact disc. Just among his many contributions, perhaps I'd like to mention a few. His work with Lijian Zhang on the diversity multiplexing trade-off has spawned many papers, as you all know, and whole sessions in this symposium, for example. His work with Stephen Hanley on multi-user detection was actually one of the first applications of random matrices in the world of wireless communications, and as you know, that has been also quite a successful endeavor. He also made very important contributions to the whole topic of scaling laws, primarily with Gross-Glauser, the whole issue of Gupta-Kumar type models, and the fact that with mobility things can improve and not be as pessimistic as originally thought. And in a way, we can consider David the father, or one of the fathers of opportunistic communications, and not only at the academic level, but if you have a 3G phone from Qualcomm, or you download a book from Amazon to your Kindle, you're actually using some of David's technology that he developed in a short span at Qualcomm. So his contributions are really span the gamut from the academic to the very applied. His book on wireless communications with Pramod Viswanath, you all know, is a bestseller in the field. And most recently, he has developed a new approach to analyze Gaussian communication systems in the high signal-to-noise ratio. And I believe, from the title of the talk, that's going to be today's topic. So, without further ado, I give you David Tse.
Can you hear me? Okay. So thank you so much, Sergio, for the very warm introduction. Thank you very much for the organizer for inviting me here. It's a great pleasure to be here because I come to ISIT every year, and it's good to be here. So, okay. So the title is It's Easier to Approximate. Let me tell you what I want to talk about. So I'm interested in network information theory. So let's see what the holy grail of network information theory is. Here we have a network of nodes. We have a bunch of sender nodes. I have a bunch of destination nodes. I'm interested in understanding how much information rate can each sender send to one or more destinations simultaneously. This is the noisy network channel coding problem. I'm also interested in putting the source into the picture. And suppose each sender observes some sources. The observations may be correlated, and they want to send these sources to one or more destinations. If I take away the network from the picture and replace all of these by just noiseless link between the source, the senders, and the destination, I have the network lossy source coding problem. If I now put the two together and put the network back into the picture together with the sources, I have joint source channel coding problem. So basically, these are the three problems I'm interested in. So we should ask the question, what constitutes an acceptable solution to this problem? So to answer that question, perhaps we should go back to Shannon. Shannon focused on the point-to-point situation with a single sender and a single destination. And he answered this question completely, as we all know. The channel coding problem is solved by an expression for the capacity, the maximum information rate. The source coding problem is solved by the rate distortion function. For a given distortion, what's the minimum rate to represent a source? And the joint source channel coding problem is solved together by the fact that the target distortion D is achievable if only if RD is less than C. So this is an exact solution to the problem in the sense that the problem was started off as an infinite dimensional coding problem because you don't have any constraint on block length. However, the solution is exact and finite dimensional optimization problem. And in many cases, for specific channels, they can be solved in closed form. So this solution is remarkable. And it's a bit of a, I think, double-edged sword for our field. In a sense, it stimulates our entire field, but at the same time, makes life very difficult for us because it sets a very high bar. In fact, if you look at engineering fields, there are not that many engineering fields where optimization problem can be solved such cleanly and exactly. So let's see how much progress we've made over the years in the network problem, the network version of this problem. So the first success came in 1970s, the so-called multiple access problem, where now you have two senders or more senders simultaneously sending to a receiver through a noisy channel. And as is well known, the capacity region is solved, characterized by three mutual information expressions for two users. In general, 2k-1 constraint, the famous pentagon. The result is by El-Shwedi and Liao. And this result is remarkable in the sense that it holds for any number of users and for general channel model. So, starting with the multiple access, we have the whole world of network IT problems that we stated in the beginning. How have we gone since then? The next natural problem is, of course, the reverse problem, which is the broadcast problem. You have a single sender want to send to multiple destinations. And this problem was first formulated by Covert in 1972, and he made seminal progress on this problem. However, the general problem remains open for 40 years. So even a seemingly simple problem is open for 40 years. And if you look at the field, I would argue that since the multiple access result, there has not been any such general results in network information theory. Most progress has been made on looking at very small problems, like two users, or very specific channel models. So one particular class of channel models that is of interest is the so-called Gaussian channel models, or Gaussian source models. So we have a big empty question mark out here. And let's see if we now make the further structure assumption that you have Gaussian sources or Gaussian channel, how much more progress can we make? So Gaussian problems, why are we interested in them? They're practically relevant. In terms of channel, we're interested in, say, wireless communication networks. Gaussian models, linear additive channels, pretty reasonable model. Physically meaningful, I think it's good to look at problems that are physically meaningful because they give you a structure which is defined by nature, and often nature is kind to us, and we should exploit the kindness of nature. Also, they provide worst-case bounds to many problems that are non-Gaussian. So these three reasons, I think, are quite sufficient to focus a lot of attention on these class of problems. The question, though, is, are they really easier? Okay, so now let's look at the world of Gaussian network information theory problems. The multiple access is, of course, solved because it's solved in general. The broadcast received a lot of benefit from the Gaussian assumption. And lots of progress have been made on the broadcast problem. And I won't go there. Why? Because Shlomo, 2 years ago, has already done an effectively exhaustive discussion on this problem. But let's look at other problems. There are many other problems. Let's see how well they have been solved under the Gaussian assumption. So we have 4 problems here. Pretty simple problems, basic problems. Interference, relay, multiple description, distributed lossy compression. 2 are channel coding problems, 2 are source coding problems. All these 4 problems are very basic. Bad news, none of them is solved in general. General means general number of users. So even if we make this physically nice assumption of Gaussianness, we're still pretty stuck. I think that's a pretty reasonable conclusion, given so many years, man-years of effort on these problems, so many problems out there, and we only were able to solve essentially 2 problems in general. We're pretty stuck. So how do we go from here? So the strategy that I propose is approximation. So engineers approximate. We are engineers, so we should approximate. So, however, since we're also theorists, we're not interested in only giving some heuristically approximate solution. We're interested in giving approximate solutions for which we can give a performance guarantee on how far we are from optimality, so that we know how much progress we've made and how much more progress we can make. Now, approximation results are not new. I'm not claiming that we're the first people here to talk about approximation results, but the approach I'm advocating here is a systematic approach which applies to many problems. So the earlier approximation results are basically isolated results. We're advocating a systematic approach. So I want to talk about a specific approximation approach here. Certainly, depending on your approximation criteria, you can have different approximation approach. But I want to talk about one specific one to be concrete and which I think is quite promising. So the approach is the following. First, I simplify. We simplify the given Gaussian problem in the following way. In the world of channel coding, we convert the noisy problem, we simplify noisy problem, to noiseless problem, deterministic problem. In other words, deterministic channel. In the source coding world, we simplify the lossy problem to lossless problem. Notice that they rhyme. Second step, we analyze the simplified problem. From the simplified problem solution, Insights is used to find either new schemes or new outer bounds for the Gaussian problem. And then we compute a worst-case gap to see how well we're doing. So that's the approach. Okay, so one asks the question, which is, why are we interested in simplifying to noiseless and lossless problem? Well, noiseless is typically easier than noisy. Give you an example. Here's the broadcast channel problem that we talk about in general. Open for 40 years, as I mentioned. However, if we put the further assumption that the channel is a deterministic function of the input, okay, then it's solved independently by Martin and Pinsker. So a very difficult problem is made solvable by this deterministic noiseless assumption. The dual problem is that lossless is easier than lossy. And what is the dual problem to the broadcast channel, deterministic? Anyone know? Audience participation. Anyone knows what the dual problem is? Slepian-Wolf. So the lossy problem is the problem of distributed source compression. You take two sources, y1, y2, y1, y2, and you encode them distributedly to convey to a central decoder, which is interested in reconstructing y1, y2 up to certain distortion d1, d2. The general problem is open. When the distortion is 0, that is lossless, solved by Slepian-Wolf. Okay? So we can see that lossless is easier than lossy. So we want to exploit the easiness of these two problems in our approximation approach. So the goal of the talk is very simple. I start with this world of blue and red. And as we know, since I'm from Berkeley, I'm interested in converting red to blue. And that's what I'm going to try to do. Okay? So we start with the first problem. The 4 red dot here is the interference problem. So in this problem, we have 2 senders and 2 receivers. Okay? And with crosstalk between them. Sender 1 is interested in sending a message M1 to receiver 1. Sender 2 is M1 send receive message to M2 to receiver 2. This is the classic interference channel problem. 2 independent messages interfering with each other. We want to know what the simultaneous capacity region is. Let's look at the progress we made on this problem. The first case that was solved is the so-called strong interference problem. So the strong interference problem is basically that each user's signal is heard louder at the other guy than your guy. Okay? So how do we solve this problem? We made this observation. Okay? In a working system, that is, if I have a system which works, which can decode the respective messages, I argue that the message M1 is actually decodable at receiver 2. So receiver 2 is not interested in M1, it's interested in M2. But automatically, it can decode M1. And why is that? Number 1, it can decode M2 because it's a working system, and it's interested in M2. After it subtracts M2, it has a very strong link to M1. In fact, stronger than the link for its own receiver. Since its own receiver can decode M1, this guy must also decode M1 as well. And so therefore, automatically, M1 becomes a public message. That is decodable by both its own guy and the other guy. Similarly, M2 is decodable at the other guy, and so both messages are public. Once you recognize that, then you can prove the following theorem. The 2 messages are simultaneously decodable at each of the receiver, and therefore they must satisfy the MAC constraints, multiple access constraint at each receiver. And so the capacity region is just the intersection of the 2 MACs. Okay? So we have Hana-Kobayashi 81 Sato 81 independently solved this problem. Now, what does that mean to a coding person? How does this change the coding picture? All right, so in a point-to-point link, I have my Gaussian code words sending over this channel, and I want to make sure that the noise balls don't touch. However, if I have interference, the other guy's trying to do the same thing. This is no good because his signal is going to interfere with my signal, and the noise balls start overlapping. To make it public, essentially I want to make sure that everyone can decode all messages. And so the sum of the code words must be spaced apart by the noise balls. And so therefore, the individual code book of each transmitter should be spaced far apart. So from the coding problem point of view, it's essentially identical to the point-to-point problem, except that you have to load the data rate to accommodate the other guy. The code book structure is identical. Load the rate, though. Okay? Now, let's see what happens in the weak interference case. So this is the case when the point-to-point link is stronger than the direct link is stronger than the cross-link. Okay? In this case, it's too inefficient to make the messages public. Because if you want to make your message decodable with the other guy, and since the cross-link is weak, then your data rate has to be lowered way too much. And so this is obviously not an optimal solution. What is an optimal solution? In other words, how can the two transmitters code the information so that they can efficiently coexist on this interfering environment? Open problem for 30 years. Okay? So this is sort of the first problem that we encountered, and we're really curious about this problem. Why is it so difficult? And so we look at the literature and say, actually, how many interference channel problems are actually solved? Well, it turns out to be easy to search for that, because there's only one problem that was solved, basically. And this one problem is the so-called deterministic interference channel, solved by Al-Gamal and Costa in 1982. So this is the following problem. The channels are all deterministic function of the input. Okay? And this determinism has a special structure. The cross-link goes through a signal G1, gets you a signal V1, mixed with your own signal through a function F2, arrives at decoder 2. Similarly for decoder 1. So the key to solving this problem turns out to make a certain assumption on the function G1, G2. And the key assumption is that given x2 and y2, the entropy of V1 is 0. Which means that if I know my transmit signal and my receive signal at receiver 2, then I can figure out exactly what V1 is. Okay, that seems like an innocuous assumption, and it is an assumption because it puts a structure on the determinism of the channel. But this assumption makes the problem solvable. And similarly, you make an assumption on V2. So the key observation is the following. In a working system, the component of M1 on V1 is decodable by receiver 2. So this is an analogous statement to the strong interference channel, except now you're not guaranteed to decode M1, the entire message. However, because you can decode your own message, you have a clear view of V1. And therefore, whatever the sender 1 puts on V1, you can immediately see and decode. And so that part automatically becomes public. And that's the key fact that enables them to show the following fact. That is a scheme which looks like this. We have two parts to your message, A and B, blue and brown for transmitter 1, and blue and orange or pink for transmitter 2. You split into private and public. And the decoder 1 decodes both A and B, the public messages. Okay? And also decode your own private message, but ignore the other guy's private message, treating that as noise. So this is the so-called Hanen-Kobayashi scheme proposed in 1981, same paper as earlier. this scheme is optimal. Okay? Now, you may ask, so what? Who cares about this particular deterministic channel? In fact, if you look at this problem, it seems that the authors have cleverly invented the problem to solve a problem they want to solve. They want to solve the problem that High and Kobayashi is optimal, and so what channel can make High and Kobayashi optimal? Reverse engineering, which is what we all do. Okay? Turns out, though, that the insight is much deeper than that. Turns out that there's a connection to the Gaussian problem. And here's the connection. And the connection is basically trying to understand whether there's a natural V1, the public part, to the transmitter. To the public part, V1, in the Gaussian problem corresponds to the deterministic channel. Is there a natural V1? So to do that, let's do a binary expansion on this transmit signal x1. Okay? So let's look at this binary expansion, and let's see what happens to this real number as it gets through the cross-link. Okay? When it gets through the cross-link, it will be attenuated by the channel, and say shifted, the decimal place is shifted 2 points here. B1, B2. I don't know why my laser pointer is, oh, it is working, but you have to look carefully. B1, B2 dot, so 2 decimal points, and then followed by B3, B4, B5. Now, if we normalize our noise to be unit variance, then we can approximately think about the problem as the following. If this signal is received at the decoder, receiver 2, then because of the noise, the bits B3, B4, B5 is no longer very visible. It's garbled by the noise. So to a first-order approximation, we can think of these bits as gone. The rest of the bits, though, is above noise level and therefore visible. Okay? So now, remember what V1 is in the deterministic channel. V1 was the visible part that can be figured out from transmitter 1, from receiver 2, if it knows its own transmit signal. So here, if it knows its own transmit signal, then it can see B1 and B2 because it's above noise level. It can subtract its own signal away and now get a clear view of B1, B2. So a natural identification is that B1, B2 should be public V1. Now its own receiver is stronger, so it sees more significant bits, B1, B2, B3, B4. B5, etc. is hidden in noise level. So therefore, there is an extra part, B3, B4, which is visible at its own receiver, but not very visible at the other guy. Now, of course, because of the noise randomness, this visible, invisible is only an approximate statement. And that's where the approximation comes from. Okay? But now we have a natural correspondence, and we can construct a natural deterministic channel model that approximates the Gaussian model by essentially rounding my received signal here, H1 to X1, at the noise level, which is 1 here, normalized to be 1. So I take the nearest integer, okay? And the received signal Y2 is just the sum of that contribution from the cross-link and my own signal, also rounded off. And this is a deterministic channel, and exactly satisfies the Elgamal-Costa assumption. And this is our bridge to Elgamal-Costa. So once we realize this connection, then there's a natural strategy now for the Gaussian problem, which is I use High and Kobayashi idea. I split the messages into public and private, both a Gaussian code word, but now I want to make the private nearly invisible at the other receiver. How do I do that? I set the power of it so that it's received at the noise level at the other receiver. Okay? And so what's the picture now? The picture is now the following. First, I put my private message, my points. These are the stuff I can hide away from the other receiver because it appears at the noise level at the other receiver, Y2. Okay? But at its own receiver, because it's a stronger channel, it can see those points, so convey information. On top of that, it superimposes a common message, which is like the original strong interference channel spaced apart to avoid collision with the other guy's common message. So now, the code is really different from the point-to-point code because this code is multi-level. It has two scales to it. One, the private scale, and two, the common scale. Okay? And we showed that, indeed, this strategy can achieve capacity of the interference channel to within 1 bit per second per hertz. Okay? So this is an approximation result. We don't have a scheme which achieves exactly the capacity, but it's within 1 bit per second per hertz. And when is this kind of result relevant? When the data rate is high. And when is the data rate high? When the noise is small compared to the interference signal. In other words, interference-limited regimes. On the other hand, this is not an asymptotic result. It's a result for all values of the channel parameters. And this is what I meant by a performance guarantee. So now we can ask the question, which is, well, we've shown that the Hahn-Kobayashi strategy is actually pretty good. And this is an existing strategy. So we're not, in some sense, we're only verifying that some known strategy is good, or on the other, although we put some special structure in it, but still a known strategy. Question is, can this approach actually discover new schemes? And here's an example in which it does. So in this example, you have many users interfering with one user, many to one interference channel. And let's look at what happens. Again, I do the binary expansion for transmitter 2, shifted to B1, B2, B3, B4, B5 are at noise level. And therefore, I can remove that because I'm not going to convey bits to it anyway. You do the same thing for user 3. So you send C1, C2. You zero out the significant bits that are below noise level at the receiver. That conveys no information. Don't send anything there. Now, let's see what kind of interference they cause. They add up to B1, B2, all 0, plus C1, C2, all 0. There's something good about this problem. Is that now the two interference is aligned to each other. So this is the concept of interference alignment, in the sense that the bits are aligned together so that each one of them is causing interference anyway. So if both cause interference, it's not going to cause any further harm. Okay? So to take advantage of this structure, I need to make sure that I can translate this to a good scheme for the Gaussian problem. And let's see how a Hahn-Kobayashi strategy would do here. So a Hahn-Kobayashi strategy, okay, so I want to send, A1, A2, A3 below those interference to get A1, A2, A3 for user 1. Now a Hahn-Kobayashi strategy would choose some random Gaussian code at each transmitter, sends it. When you add it, so what happens when you add two random Gaussian codes? You get another random code. But this one is really random because you're adding a bunch of things together. So therefore, you left some space between these points for user 1, each one of them. But when you add them, the space closes off. So therefore, random codes cannot keep that binary expansion structure that we had for deterministic thinking. And so therefore, when user 1 wants to send in the holes, there are no holes, so everything got clobbered. So there's a natural solution to this. Instead of using Gaussian code, we could use structured code, where you use the same ladders at the two transmitter, such that when you add the two ladders together, you get another ladders with the same spacing. Now there are enough holes for transmitter 1 to send. Okay? So this suggests that, indeed, you can achieve capacity to within a constant gap, but not using Gaussian random codes, as in Hahn-Kobayashi, but using structured code. So this is a first instance that this approach actually could produce new schemes that was not known before. Okay. Open question. Find a constant gap approximation to the general K user interference channel for K greater than 3. I looked at the many to 1 case, and if you have a solution at the end of this plenary talk, please come to me, and I'll give you $1. Okay. Hard problem, hard problem. You have a solution already? I heard someone say. Okay. So the second problem I want to look at is relay. Okay? So in this case, I have a single source, single destination. Okay? And I want to send it to a receiver, single source, single destination, through a bunch of relays, signals superimposed on each other. Again, the capacity is open for 30 years, even for a single relay. Okay, even with one relay is open. Best known achievable strategy by Culver and Algama. You see a theme here is that every once in a while, it's always these people again. Annoying. Neighbors. Good neighbors. All right. Now, how do we solve this problem? So it seems like we're really ambitious here because the single relay is not even known, and we're trying to solve the whole network of a bunch of relay nodes. How do we solve this problem? To solve this problem, we need to do approximation. So the one case that we know how to solve for this problem is when the network is wide-line. That means all links are orthogonal and no noise. Max flow min-cut theorem by Ford Fulkerson in 1956 tells us that the capacity is the minimum over all cuts omega of the sum of the capacitive lengths crossing that cut. Very nice theorem. Can we prove such a theorem for the Gaussian case? Well, we have the cusset upper bound. This is analogous to the min cut. It is minimum of all cuts, the mutual information across the cut, and maximizing over all input distribution. Unfortunately, we don't know whether this is tight. We don't know what the capacity is. In fact, we don't know many things. For example, we don't know what we should forward at each relay. We don't quite know how to forward. So let's try to answer these two questions. What to forward and how to forward. Okay? So we get the inspiration from wide-line. In the wide-line case, every bit that each relay receives is good. There's no noise. How about the Gaussian case? Is every stuff you receive good? No. We learned from the interference channel that there are actually two parts to the signal. The one above noise level and the one below noise level. Below noise level is basically junk. It's no good. So, to a first-order approximation, let's do that. Let's just quantize the received signal at each relay at noise level. And now these are reasonable bits, good bits, approximately good bits. So then this suggests a natural deterministic channel, which is like the one we use for the interference channel, where I take the received signal at each relay, I run it off to the nearest integer, and I get rid of the noise. And I get a deterministic network now. This deterministic network is a bridge between the wide line and the Gaussian network. Okay? So that's the first question. What to forward? I want to forward the bits above noise level at each relay. How to forward? In the wide line case, Ford Fulkerson tells you that you should route those bits forward. But in our case, it's kind of complicated because things are adding on top of each other. They're broadcast, so you get multiple copies of stuff everywhere. So it's a little bit complicated. We don't know what routing solution to use here. However, there are these folks which give us a way out. Al-Shwedi, Kai, Lee, and Young says that information theorists are lazy people. We don't have to care about algorithms, routing algorithms. All we have to do is to do something random and hope for the best. And that's what they said. If you do random coding, in other words, in a wireline network, if you mix up all your packets you received and send it out, with high probability you'll be OK. So this gives us a way out. Because now we can have an analogous thing to do. We quantize the signal, and now we just randomly map that quantized signal to a Gaussian code word, which I transmit over my link going forward. That's it. Is this strategy good? So starting with our Shwedi, Kai, Lee, and Young result is for wide line. We used a deterministic network as a bridge so that we can prove an analogous result for the deterministic network. And then we add back the noise into the picture, and then we prove a result for the Gaussian network. So that's the bridge. And so we prove this theorem. quantized and random map, the strategy I said, can achieve within a constant gap to the capacity, sorry, not to the capacity, of course, to the cut step bound, where the gap doesn't depend on the channel gains. So this is an approximate max flow min cut theorem, because we're not saying that the cut step bound can be achieved. We're saying that you can universally approximate the cut step bound, universal over all the channel parameters, all the channel gains values that you can take on. Okay, so approximate max flow min cut. Now you may say, geez, maybe many schemes have this property, and our scheme is only one of them, and so it's not very interesting. Not true. Turns out all the classic schemes, decoding forward, amplifying forward, Gaussian compressing forward, do not achieve a constant gap. Now, let's be more concrete and focus on a simple example. Single relay. I have one source, one sender, one destination, one relay. Let's use our binary expansion to give a concrete feel of what we're doing here. You look at the binary expansion of transmit signal. At the final destination, you receive a shifted version of that. Noise gobble up the bits below on the right decimal point. You get B1, B2 on a direct link. The relay is trying to help out here. So what can the relay do? Suppose the relay has a stronger link from the source. So it sees B1, B2, B3, B4 above the decimal point. Noise gobble up the B5, etc. So now, if you quantize, you roughly speaking is getting B1, B2, B3, B4. Okay? And then so what you're sending out is a function of these bits, roughly. And now the decoder is going to combine the information B1, B2 receives on a direct link with the information receives on a cross link and decode the information. Now, in general, there will be noise in this phi function, because when you quantize, there'll still be some random noise which gets above noise level because of randomness. You cannot cleanly remove the randomness. What we showed is that that noise has banded effect on the performance of the system, and therefore can still achieve a constant gap. However, in this particular simple network, the destination actually has the relay has a stronger signal than the destination. And so actually the relay can actually decode the whole message and clean off the noise. And if you use this scheme, it turns out that you can compute the gap, and the gap between this scheme, decoding forward, and the outer bound, the cut step bound, is at most 1 bit per second per hertz. Okay? So this is a specific case of our result, specialized to the single relay case, but taking advantage of the structure to do decoding forward. In general, if you have a network, any single relay may not get a view of the whole picture, and therefore they cannot decode the whole message. Everyone gets bits and pieces of what's going on. And in that case, then our scheme would work in general, whereas decoding forward would not work in general. So I gave you the good news. Of course, I'll leave the bad news to the last. I'm a good salesman, I guess. A bit of a bad news. This kappa gap actually increases with the number of nodes. So our result is meaningful if you have a small number of relay, but when the number of relay gets larger and larger, the gap grows with it. And a simple reason, because we're quantizing and forwarding, so therefore noise is getting into our signal. And this noise will be accumulated as you relay more and more stages, they'll kill you more and more. So this result is not scalable with the network size. It's universal in the channel gains, but not universal in the network size. Open question. Is the gap of the capacity from the cut step bound universal of the number of nodes also? We showed that the gap of the capacity of the cut step bound is universal in the channel value parameter. But is it universal in the number of nodes? If so, find a scheme. If not, find a better bound, which is universal. Open question. OK. So now we're done with interference, relay, the two fundamental problems in channel coding. Let's move on to source coding. OK? So what did we do in channel coding? We have this picture. I have a binary expansion of my signal. It went through the channel, attenuated, noise gobbled off the LSBs, least significant bits. And we approximate this by removing the remnants of the noise and just treat those bits below the decimal point as useless, disappear. And so I have a deterministic channel. Okay? Now, this is a conversion from noisy to noiseless. What is a duo, source coding duo, to this approximation? I start with a Gaussian source, and I want to reconstruct that Gaussian source with a certain distortion D. So I can do a binary expansion on X again. It seems that the only thing I know how to do is binary expansion. Turns out to be quite useful. What does it mean when I want to reconstruct X to a certain distortion D? It means that I don't really care about the bits that are less significant than a certain level. And I don't have to worry about them. All I want to do is to reconstruct, say, the first 2 significant bits or the first 3 significant bits, depending on my distortion target. And therefore, for each distortion target, I can now convert the lossy problem to a lossless problem. Because my goal is just to reconstruct B1, B2. Exactly. Lossy problem. Lossless problem. So let's use this construction and apply it on 2 problems. This is the multiple description problem. In this problem, you have a single source, X, Gaussian source. I have 2 encoders. I want to create 2 descriptions of this source, 2 or more descriptions of this source. Description 1 is intended for decoder 1 to be reconstructed with distortion, say, D1A. Description 2 is intended for decoder 1B to reconstruct with distortion D1B. Now, think of these as 2 packets. This means that if you get one of those packets, you get a certain reasonable reconstruction of the source. But if you happen to be lucky enough to get 2 packets, I want you to get a better distortion, and that's D2 for decoder 2. So decoder 2 is what happens when you get both packets. So this is a very common problem in source coding. So when there are k equals 2 description, like in this figure, it's solved by Ozerov in 1980. But when there are more than 2 description, problem is open, completely open. No one knows what the rate region is. By the way, what I mean by solved, I mean that if I give you distortion requirements, you tell me what the feasible rates that you need to create those 2 descriptions, or 3 descriptions, or 4 descriptions. So obviously, this is a very high-dimensional problem as you get to more description. So let's simplify it a little bit so that we can focus on the essence of the problem. Let's focus on the symmetric case. So here, I want the same distortion, D sub m, for any subset of m descriptions. That means as long as I get m packets, I don't care which m, I want a certain distortion, target distortion. So reasonable formulation of the problem. So in the example here, a symmetric K corresponds to D1A when you have one description, equals D1B when you have another description. D2, on the other hand, is usually smaller than D1A and D1B. Okay, so to solve this problem, let's convert the lossy problem to a lossless problem. Okay? So binary expansion of X. The decoder 1A wants to reconstruct with a distortion D1, say the first 2 bits, B1, B2. Decoder 1B wants to reconstruct the same first 2 bits because it wants the same distortion, D1. Decoder 2, the central decoder, wants a good description of a good distortion, so it wants to reconstruct, say, up to 5 significant bits, B1, B2, B3, B4, B5. So now I have a lossy problem. Now I have a lossless problem. What's the lossless problem? I group my bits into two groups, MSBs and LSBs. I don't care about B6, B7, B8 here, because none of the decoder wants it. So I can throw that out of the picture. So now I have this problem. I'm giving you two random variables discrete, V1, V2. The decoder wants to reconstruct, decoder 1 wants to reconstruct V1. Decoder 1A, sorry, typo here. 1A wants to reconstruct V1. 1B also wants to reconstruct V1 with distortion 0. And description, this decoder 2 wants to reconstruct both V1 and V2. Now notice that nobody wants to reconstruct just V2. That's silly, because that's the least significant bits. There's no use for least significant bits if you don't have most significant bits. Okay. How do we solve this problem? Okay, it turns out someone solved this problem already. Okay. Again, this Raymond Young guy. Annoying. And I heard that he's talking tomorrow too. Okay. All right. So this is a so-called multi-level diversity coding problem. Okay. And the solution of this, or the problem I should say first, in general, is I want to reconstruct a sequence of random variables, V1, V2, up to Vm, from any subset of M description. There's a degraded ordering. I always want to reconstruct the MSB, always, and then maybe more bits if I get more packets, more description. Okay, good. How do I solve this symmetric multi-level diversity coding problem? Actually, the solution is pretty intuitive. I have, remember, V1, V2, V3, going from MSBs to LSBs. I want to create three descriptions to carry information about V1, V2, V3. Okay, so V1 is the MSB, very important. Any description by itself should be able to reconstruct V1. So the coding is trivial. I have to repeat this blue 3 times through a 3-1 repetition code. V2, on the other hand, is supposed to be reconstructed whenever I get 2 descriptions or more. So therefore, I can do coding now. In fact, it's obvious what I should do. I should do a MDS code such that whenever I have 2 descriptions, I can reconstruct both the data packets. Okay? So this is 3-2 MDS code. And finally, at the top level, it's only useful when I get all 3 descriptions. So I don't need to do any coding because I get all 3 descriptions anyway. So I do a free no coding. That's it. That's the solution of the multi-user diversity coding problem. Now, I can now put it together and go back to the lossy problem. There's a very natural solution. In fact, my colleagues tell me that Microsoft is trying to implement something like this. I have a successive refinement code. I use a successive refinement code to generate my V1, V2, V3. What is the successive refinement code? It's essentially giving me multiple layers, and these layers essentially contain MSB, next MSBs, and LSBs, V1, V2, V3. And now I do a multi-level diversity coding on V1, V2, V3. I get this, and that's it. Now, the question, though, is this any good? Our intuition says it should be OK, but one has to do the work. These folks done the work. Not so easy work, I must say. They showed that this scheme can achieve within 1.48 bits per sample of the symmetric rate point for any number of descriptions. Symmetric rate point corresponds to the point where all the rates R1, R2, R3 is the same. And in general, they showed that this scheme is within a constant gap to the general rate region. Okay? Now, turns out that this scheme is not optimal. There's a better scheme which can achieve a better gap of 0.92 bits. Basically, the better scheme works like this intuitively. It says that, well, if you get all three description, you get all three of the middle layer. But all three of the middle layer is no better than only two. Because if you do MDS code, if you get three packets, you're not going to get any more information. What they do is they want to provide more information to get better things. And their scheme turns out, again proved by these Tien, Mahendra, and Degavi, to have a better gap of 0.92 bits. So you can see that this approach not only gives you a guarantee in performance, but also tells you sort of how much better is one scheme over another. Good. So let me finish by talking about the last problem. Can I take 5 more minutes? Is it OK? 5 more minutes? OK. So in this problem, I have I already said, two sources, reconstructed with distortion D1, D2. Rate region is open in general, but solved recently for two sources. And they show that if you do random, quantize, and bin, that's optimal. Okay? In other words, you quantize each source, and then you bin them, optimal. What about for 3 or more sources? So we looked at a problem where you have 3 sources, but they have a tree structure. That is, they're all related by a random variable x, degraded version of that. So you do a binary expansion, then you see this kind of structure where they share some MSBs in common. The reconstruction wants to get a certain subset of those MSBs. Okay? So now it's pretty obvious what the right scheme is to do. Each encoder should first quantize to the target distortion and gets the bits, roughly A1, A2, C1. And this guy gets A1, A2. This guy gets A1, A2, A3, A4. There's a lot of redundancy here, so you do a binning to get rid of the redundancy. And indeed, this strategy can achieve the rate region to within a constant gap. Now, is this true for all sources or for all triple sources? Turns out not the case. Let's quickly see this. I again have 3 sources, but it's not a tree source anymore. The third source is the difference between Y1 and Y2. Y1 and Y2 has some common bits in common. It's correlated. And the decoder is interested in reconstructing just Y3 for simplicity. And I'm interested in determining the rate region of R1 and R2 to get there. So Y1 and Y, the difference between the two guys is like this. Okay? Now, for a certain distortion D, it's not interested in the bits on the right of the distortion. But in this problem, it's also not interested in the blue bits, because you're only interested in difference. They're the same anyway, so there's no point. So all I'm interested in is the bits in the middle, unlike the earlier problem. So how does quantize and bin work? Let's try the same strategy. So you quantize, you get a bunch of bits. You quantize, you get a bunch of bits. And Slapin-Wolf coding would remove the redundancy between A1, A2, A3. But in fact, I don't even want to remove the redundancy. I don't want even a single version of A1, A2, A3, because I don't care. So to do that, I need to avoid getting A1, A2, A3. A random quantizer will not work because it mixes all these bits together. Only when you reconstruct it, you can see it. But I want the encoder to be able to extract out B1, B2. So a natural scheme, which is analogous to our many-to-one interference channel, is to use a structured quantizer now with a coarse lattice and a fine lattice. And then I can use the fine lattice value to denote B1, B2, and C1, C2. And now I can forget about sending A1, A2, A3. I just send the index of the fine quantizer. Okay? And this was done by these folks. Turns out that Aaron Wagner showed that structure, quantize, and bin can achieve within 1 bit. So you can see the duality between source and channel coding in terms of this MSB, LSB picture. OK, let's quickly conclude. I see that Sergio is very impatient with me. What is the state of affairs? Exact solution. Pretty much the same as 30 years ago. We haven't solved too many new problems beyond the multiple access and broadcast. Exactly. Approximate solution, we have made progress. Some are solved, some are partially solved to within a constant gap guarantee. So we get two things out of this approach, I think. When we are stuck at very difficult individual problems, trying to solve them exactly, we're just stuck. Everything is difficult to us because we can't solve anything. But now, once you can start approximate things, then you can divide problems into multiple levels. Finer discretization. Some problems are easier than others because they're easier to approximate. So now you're getting a sense of the landscape in terms of the easiness of the problem or more difficult problems. That's number one we got. Number two, now we're understanding more about the connection between different problems, between lossy problems and lossless problems, between network coding on wireline and Gaussian wireless network. So now we're understanding structure between problems, and that's a good thing because progress in one area can now give us progress in another area potentially. So we are essentially trying to use this approximation approach to move from looking at the trees in the forest, individual problems, to look at the forest itself. We only have a very small glimpse right now, but hopefully we'll get a better glimpse in a few years. Okay, good. Thank you very much.
Thank you very much, David, for a crystal clear talk. We have time for questions, but not a lot of time. Let's see if there are any comments. Well, you know, if you were to play the role of devil's advocate, maybe you could say that in the real world, for the kind of network sizes and signal-to-noise ratios that one faces in reality, perhaps the state of affairs is a bit too conservative. So you may have these bounds are still far away from the best one could do.
So as you saw in the relay example, the worst case bound is say 1 bit. But since this approach gives us upper bounds and lower bounds which are computable, in the general case, it's actually much less than 1 bit. So often these bounds are themselves conservative already.
Right.
So that's one thing. Number two is that you can improve the bound. For example, the last example showed that the two schemes, the multiple description, some gives better bound than others. For example, the 0.92 bits versus 1.5 bits. 3, sometimes if you get lucky enough, you can actually use some of these bounds to build on top of that and solve for exact results. Like the 2-user Gaussian interference channel, very weak interference case that I forgot to mention because I didn't have time. So I think sort of, in some sense, we're saying the final goal is extremely difficult. Let's set up intermediate milestones to go towards that goal. And if we get there, it's good. If we don't get there, at least we made it partially there.
Okay. Well, if there are no more questions, then let's thank David once more.